Right, so this is the Mambo flight control system, and here is the block diagram that we have of the flight control system, and it comprises of a set point generator here, flight controller here, Simulink model of the drone here, state estimator here, and a display module here. Now the only bit we play about with is this one here, which is the control one. And these are typical outputs that we'll get when we've run the simulation. This is a change in height of 1 meter, slightly damped, so getting a response. This is the change in x, it's very small, 10 to the minus 3. Change in y, 10 to the minus 3, and the pitch. We can change what variables we want plot here, but this is a typical thing that we get out. Now, before we start, the first thing you need to do is go to MATLAB and go on to add-ons. So if we click on add-ons and get add-ons, then it comes up with the screen here, and if you type in at this parrot and then choose then the Simulink support package for Parrot mini drones, the one with a little Simulink block diagram. I've installed mine already, so I can't reinstall it, but if you click on this, then instead of manage here, it'll have install. So mine is manage, so I've got options, but because I've installed it, I can't install it again. So then you can then click on here and install it, or whatever you want. So that's the first thing to do, and then when you've done that, your package will be installed. Then the next thing to do is to type in at the MATLAB command prompt here. Now there's a certain command you've got to type in, which I'm going to look for now. Oh, no, this is the wrong trick. Hang on. Go into sent, and the command you want is parrot. No, you don't want that one. It's not the one we want. No, I can't find it. I think it's parrot mini drone hover. Now you might need to, it's like I've got it in a Word document somewhere. It's not very good. You have to type in a command here now at the command line prompt, which is going to be parrot mini drone hover, like this. Parrot and capital M mini drone, all in lowercase. You can't see this, can you? I don't think I can move it either. Yeah. Parrot mini drone, then a capital H hover. So you're going to type in parrot mini drone hover, and then it will launch the Simulink simulation. Now, I've already got mine. Go in here. Mine's called something slightly different. Parrot mini drone. Mine's called Parrot mini drone orbit. The reason that it's called this is because I corrupted my Parrot mini drone hover. So sometimes, if you're not careful, you can corrupt them. So this is what it looks like, and this is the simulation here. And if we type in run there, set the simulation time here, click on that run button, it will then run a simulation of the drone. Now there's some things you might want to watch. Sometimes if you click on this little box here, you might want, this is a one that stops the simulation if it crashes. Sometimes it's better to switch this one off by just clicking on this and making that. If you click on this, you can enable it or disable it. So if you click on there, it enables, which is how it is at the start. If you click on there and do disable, then that's a good little trick to keep the thing going. And another trick I found is if you go into the visualization, then on some of these, this box here, floor contact, this one sometimes triggers and stops the simulation. So you click on that one and do it'll be enabled. It'll look like that. So if you click on that one and do and enable it, got a better chance of running your simulations then. Click on that one, it'll go back to here. So let's have a look at the thinking behind it. So we've got the underlying structure of the controller here. We can do this in Simulink as we go along actually. So what we do now is if we click on this box here, it goes down to this box, set of boxes. Now you can forget about that one, it's just this one. Click on this one now, and it comes up with this. Now there's two boxes you want to play with, this box here and this one here. Now this one allows you to change the X, Y, Z movement of the drone, the set points. Don't use anything else, it's easy to use in here. So click on this box, you've got some X, Y and Z. So I'll put X as -1 here. So remember it's positive down, so -1 is up. Now you can change these quite easily around here. You can modify this bit quite simply to put in different set points and different things. But for the moment, we'll just do a set point of 1. And if you click on that box, this is the constant value of 1. So if you click back upon here, you can go back. So that box there is the one you use to control the commands, the set points. This is where the control sits in here. So if you click on this one, these now are the different controllers. This is an altitude controller here, that's the one we're going to play with. This is your controller. This is a pitch and roll controller, and this is an XY controller. So there's like 6 controllers there, and they're all PID. I'll try and explain those here for you. So you've got a PID on height, PID on yaw, PID on pitch, PID on roll. And then you've got PIDs, 2 other PIDs on X and Y, and they feed into the pitch and roll. So by feeding in to the pitch and the roll, you can control it in X and Y. So we can look, the main ones to look at for our project are going to be the PID there, and the PID, those two are particularly easy to look at, and they work very well. We could also look at the PIDs here as well. These are part of these loops anyway. So that one and that one go together. So that one's this one's on its own, number 6. Number 5's on its own. 2 and 4 go together, and 1 and 3 go together really. So that's these are standard PIDs. If we click on the one we're going to look at for the moment, which is the height one, which is this one down here, then here's your PID gains for the height. Now originally this was set at 0.5. So if we had that set at 0.5, we'd get a certain simulation, and I've chosen 3 values here. I've kept the KP and KI constant. I've just played about with the derivative. As you lower the derivative, it gets less damped. So let's have a look at what I mean by that. We go down here, but these are the controllers. Don't need to worry about this. Oh, this is a little program I've written called Plot Mambo at 2021, and I'll send you a copy of this. If you run this program, when you've run the simulation, it plots out 4 little graphs in like a 2x2 array, plots the height, the x, the y, and the pitch. Now, which variables you plot out here depends on what you pick up from the data pool. So data number 1 is x, 2 is y, 3 is z, 4 is pitch, 5 is yaw, 6 is roll. So if I change the numbers here, you can pick up different variables, but I just go for x, y, z, and yaw. They seem to be the most sensible. And then this plots those out for you. When you run this program, you run the simulation first, then you run this program, and you'll get some graphs of the simulation, which look quite nice for a report. And this is a typical graph we've got. So this is the first one now, where I've got a proportional gain here of 0.5. So you could try running the simulation with these gains, and you should get this transient response on height. So it goes up to hold a height of 1, and this point here, it comes down and lands. It doesn't do a very good landing. I don't know why, but it doesn't, but it does land, so don't worry about it. This part here we're looking at, the shape here. The x motion's very small, 10 to the minus 3. Y motion small, 10 to the minus 3. Pitch motion, so it's quite a stable response, so critically heavily damped there. What I did then was, I then changed the gain to 0.3. So the damping's gone down now, so I've got a bit of overshoot in the drone here, a bit of overshoot there. And then drop the gain down again to 0.1, and this is the lightly damped response to the drone. This will be pretty bad response. So you can see now the PID gains directly affect the performance of the drone, and the first thing you could look at is how the PID gains in here affect the height, and you could do the same thing for yaw as well. So height and yaw are two nice ones to do. Let's have a look at the I don't know where my yaw one is. Let's go back to here. If we go up to the controller, this is the yaw one here. So double click on that one. This is the yaw, and there's your PID for the yaw. So you can choose the gains and the PID for the yaw as well. And then you can try different performances as it goes along. There's a saturation here which limits the amount it can yaw. If you make it yaw too quickly, can go a bit funny. So this has got a limit on yaw of about 30 degrees. So the maximum amount it can yaw is 30 degrees. You could make that bigger or smaller, and it would either yaw quicker or smaller. If it yaws too quick, it can destabilize itself. But there's some more games you can play with there, and then you can look at the transient response in yaw. Now to do a yaw change, you'd have to change the set point on yaw. Now to do that, you've got to play with it. This signal here would have to be modified with a set point coming onto it. I'll show you how to do that. You just go onto here and do a cut, go into Simulate Library and go on to commonly used blocks and get a summing junction. Let's get one of these, pull that over there, and then connect this up to here, and then connect that back up to there, and then to here. Now you need a step to step on yaw. Now watch, the step on yaw will be in radians, not in degrees. So if you put 1 in, it's 60 degrees, so it's quite a lot. So you only want to put a small signal in here. So we go back to here and go on to sources. At the bottom of sources, got a step, pull the step in, and connect it up like that. Now if you click on step, you can set the time. So you want it really to hover for about, say, 10 seconds. So that might be 10 then when you put the step on yaw, and the final value might only be 0.1 or something. So that means it's going to yaw now for 0.1, about 5 degrees yaw after 10 seconds. I'm just going to keep that, and then you click on OK, and then that will do a yaw for you. Let's just go back to the, it's not very light, it's quite lightly damp, this one. So we'll go back to the controller here, go to this one, and we'll put this back up to 0.5. 0.5, just to make it nice and damped. So we've got the damped height control, and we've got a yaw control coming in now. So go back to there, click now on run, and it runs the simulation. So it's running the simulation. Now, it takes a while to run. I've got an i7, and it can take a few seconds to run the simulation. My simulation doesn't seem to run very fast at all, and it's come up with an error. Oh well, so that's a bit of a shame. That's how I'm going to try and fix the error. Okay, so it didn't run. If we go back to step, we had to put in 0.005 in there. The sample time for the system is 5 milliseconds. So anywhere there's a sort of sample time, you've got to put it in. If you had something in, make sure it's 0.005. So we close that then, run this. Okay, run the simulation. And then if we go back to here and click on here now. Now, sometimes it won't come up with this. You'll have to go into home. Then, it's not done it for me. There's something called default here, screen shape. You have to choose default standard. Then it'll come up with this. Then you can load in then your plot mambo 2021 program. Go on to editor and run it. And then this is the height change here. And then at 10 seconds, it does a set point change on yaw. And this is the yaw going to 0.1, which is what we put in. So it's not that well. It's got a bit of overshoot and a bit of overshoot there. So you could tune that one to do a better yaw. If you detune this one, it'll probably have a crosstalk on this, and this will get worse. So let's have a see. That would be interesting to look at, wouldn't it? So go back to here, go up to flight control system, click on this one, put this one down to 0.2. Should we have this would change, but it's not. 0.1 is quite lightly damped, isn't it? So that's that one there. Then you click on run, runs the simulation. It takes a few minutes to run the simulation. When you've done that, then if you click on here and then run this, it'll give the graph, so you can see this is quite lightly damped here. And this hasn't got much worse, has it really? Hasn't really affected it much. So look, that's quite nice. That's your lightly damped height. And there's your yaw change there. So the first thing you want to do is then if you do edit, copy figure, then you can go into Word, say, into Word, and pop open a file and paste it in, and you've got your graphs in your Word file. So that's quite a quick way of getting into Word. Just save that. So the first thing we want to look at really is going into the flight control system, and you can play about with the PID controllers on height and see how that affects it, get some graphs, and then play about with the PID controllers on yaw, see how that affects it. I've also got some transfer functions for height and yaw, so you could then compare the performance of this drone, the simulation, with some linear transfer functions. This is a non-linear model in here. So we've got in the model, inside there, it's a non-linear model, but I've obtained some linear models which you can then use, but that's for another day. So your main thing at the moment is to be able to load in the simulation, run the simulation, go into here, change the PID gains on height and yaw, and get some transient responses out. And what you should see is there is your classical type responses. More proportional speeds it up, more derivative adds in damping. You don't probably need much I at all. So it's mostly PD control you're looking at, and you can then investigate different PD designs using the simulation. And if you can get all that to work, then you're well on with the project.